Question 4. This question is about the transition elements. For part A, when sodium hydroxide is added to an aqueous solution containing hexa aqua cobalt 2, a precipitation occurs, accompanied by color change. In your syllabus, you need to know the color change of the cobalt and these copper complexes. So for this hexa aqua cobalt 2 is actually pink color. It's something like this. You can say red. Normally we say pink. And after the sodium hydroxide added, so you will see a precipitate, a blue precipitate. So this is a change. The blue precipitate is actually the cobalt hydroxide. And now first you need to state the color change. So it's from the pink to blue. Okay, part 2 completes the ionic equations for this precipitation. So ionic equation for the precipitation. So because it's telling you hydroxide added, so you need to put hydroxide reacts with this hexa aqua cobalt 2 ion to form this precipitate. So now as you can see, the hydroxide will gain 2 hydrogen ions from this complex ion to form the H2O. So this is the reactions, okay, that normally we say precipitation because it's from precipitate. Another reactions like is asking in this part 3, this precipitation also can describe as a different type of reaction. So we know that it's acid-base. Again, why acid-base? Hydroxide, as you can see, is the proton acceptor. So it gains a proton from this water ligand here, and it's formed H2O. And after that, this precipitates form. Right? So means this complex ion is a proton donor acid, and hydroxide is a proton acceptor base. So that's why this is acid-base reaction. Part B. Okay, L is a uncharged tridentate ligand. L donates 3 lone pair to the metal atom or ion. Cobalt form octahedral complex ion E with this tridentate ligand. Complex ion E has 2 positive charge. Okay, so it's confirmed. This ligand, this tridentate ligand is charge neutral. So now you need to give the formula of E. Because it's a tridentate ligand, it will form 3 dative bonds. Octahedral only 6 coordination number, means 6 dative bonds possible. So means 2 times 3, then you get the 6 coordination number. So means when the cobalt with this tridentate ligand L, so it will just needs 2. So you just need to put this formula, cobalt L2, put the charge 2 positive. Okay, part 2, identify the oxidation state of the cobalt in E. So because this is again is neutral, the oxidation state for cobalt is of course positive 2. Actually the new syllabus oxidation state or number it should be in Roman. Okay, but for in the marking scheme it still put positive 2, so means that it will be both acceptable. Part 3. The d orbital of the cobalt atom or ion present in the E are split in energy. So d orbital now is splitting because it's from octahedral complex. Whenever there is an octahedral complex form, okay, it must be this dd splitting. So 2 orbitals will go higher, and the 3 orbitals will be lower than these 2 orbitals. So initially, these d orbitals is having the orbitals we call degenerate orbital. Degenerate orbitals means the orbitals at the same energy level. So means this 3D orbital, before is formed the dative bond, or before the ligands is form dative bonds with the metal cation. So these d orbitals, they are all degenerate. When the ligand approach and form dative bond, some of the orbitals, they will feel a greater repulsion because the ligand is donates lone pair, so it's a negative charge, or is a electrons pair. So therefore, the sum of the orbitals like the dz square and dx square y square, so they will go higher because the ligand is point to this direction. And the three orbitals like dxy, dxz, dyz, because the ligand not direct pointed to them, so feel lesser repulsion, so it will be lower energy level. So actually this part you just need to put this so the d orbitals with higher energy level, okay, there are two, okay, these two. The d orbitals at lower energy level is these three, so you just put 2 and 3, that's all. Part 4, define the term non-degenerate d orbital. Just now I told you degenerate orbital. Non-degenerate means the d orbitals must have different energy level, means the two sets here, so they are non-degenerate d orbitals, different energy levels. Part C, the mineral chromite contains a compound which has a formula, so this one is FeCrNO4. So the N number of the chromium we don't know, we need to find at the end of this part. The oxidation state for the iron is positive 2. So a sample of 4.18 gram of this sample dissolved in excess sulfuric acid, and after that the resulting solutions is made up to 250, so it's a solution F. Okay, something like this. We put the sample, okay, dissolve in the acid. Okay, when it's all dissolved, we pour the solution in the 250 cm3 VF. Okay, after that top up the water and shake it, homogenize the solution, and the solutions now we call as a solution F. So in this titration, we just need to take 25 cm3 from this 250. So means once the solution F prepare, so we need to take 25 for titrations. After titration, this is the volumes that obtained. So the KMnO4 that used is 18.7 cm3, and the concentration of the KMnO4 is 0.02. So from these two we can calculate the mole, the moles of KMnO4. Okay, so later we discuss about that. 1 mole of this manganese ion, or this KMnO4, so reacts with the 5 iron 2 ion. Assume no other oxidation occur. First part, write an equations for the reactions of the iron 2 and this manganese 7 ion. For this one, if you want to construct the balanced full equation, you can do this. If you have time, you do that. Normally we no need to do this. I just show you how to do it. First, you need to start from this manganese 7 ion, and if you reduce to the manganese 2 ion, after that you have to balance the elements. So first we balance oxygen. So on the right hand side we put the H2O. So because 4 oxygen here, so we need to put 4 H2O. Then we need to balance the hydrogens by adding the hydrogen ion on the left hand side. So here there are 8 hydrogen, so we need to put 8H plus. So at the end, when all the elements balance, we need to balance the charge. So on the right hand side is positive 2, we need to make sure left hand side also positive 2. So therefore need to add 5 electrons here, make sure is total the charge is positive 2, or the numbers is positive 2. And after that, iron 2 oxidized to iron 3. This one is easy because it's 5 electrons here, so means it's need to times 5 for all, right? Because iron 2 to form iron 3 release 1 electron. Because we want to make the same numbers of electrons here, 5 electron, so we need times 5. Okay, once it's done, then you can combine these two. Okay, this one cut. So you just put just sum up those species, left to left, right to right. So you get this equation. So this is how you get the overall equation. Now part 2. Calculates the numbers of moles of iron 2 ions in the 25 cm³ of the solution F. So then we need to use the volume of the manganate 7 ion. So it's use MV over 1000, we get this mole. So the mole of this iron 2 is 5 times larger. You see, 1 to 5 here. So therefore, the moles of iron 2 is 1.87 times 10 power negative 3. So this is a mole. Then calculate the molar mass of the sample. Use your answer to deduce the value of N. This part you have to be careful because now it's asked you to calculate the total moles of the iron 2. In the titration, this is 25. In this part 3 is total mole, means the total moles in the VF 250. So you need to convert a bit here. So use the moles that you obtain in part 2. So you need to times this ratio. Then 250 over 25 means 10 times larger. So use this mole now for the calculation. 4.18 gram given here, the sample mass. So mass over mole. So you get this molar mass. Once you get the molar mass, then you can get the N number. So find out the mass for the iron, chromium, and oxygen. So this, and this. So then you can get N. N you should get 2. Okay, that's all. Thank you.